I also saw Rhonda. Rhonda Morgan online. Rhonda is going to be actually there physically on the day, and I'll be supporting remotely. So Melanie, how does this usually go? Do I just like share screen and walk through the whole thing, or
Absolutely, yeah,
yeah.
that's how that works.
Okay, fantastic. So I will do that. Um, okay. Okay, so you all should have gotten a link to the instructions, right? By the way, if people feel comfortable doing so, it's nice to see faces. So if you're comfortable, please turn on your camera. If not, that's fine. But otherwise, I'm just talking to a bunch of text names. Okay. So yeah, if you scroll down here to the session 3, this first link takes you to the setup notebook that Melanie wrote, which looks like this. And then you should be executing all of the cells that are this color, which is green, question mark. Sorry, I'm colorblind.
Sorry, it's for the regular people, it's orange and blue, but yes, whatever you
Orange.
can.
No. Okay, so I will remember from now on. Okay, so yes, so if you're doing the collab route, which I assume the majority of people will be doing, you run the orange ones. If you're doing offline, you run the blue ones. I'll be showing the collab version. They should be essentially identical, hopefully. So yeah, so you run this sequence of cells, and what this should do, the first one mounts Google Drive. So first you'll get the scary message about this being an untrusted notebook, and you click OK. It's okay, you can trust me. I won't steal all of your personal information. Then it will ask for permission to mount Google Drive, and so you mount that. And then finally, once you get to here, it will attempt to create a directory within Google Drive and clone the repository into it. If you've already done this once, then it'll throw an error at this point, but that's okay, because that just means that you've already cloned the repository. So I'm going to give, and then if you're going the collab route, you stop at this point and you don't need to execute anything else. So I'll give people a few minutes to get through this. People should pipe up if they're having any issues at this point.
Dmitry, a user did ask if you can make the screen a little bigger. I don't know if that it works for you.
How's that?
That looks good for me.
Can people read? Thumbs up, thumbs down. All right. So whenever everybody's gotten to the end, if maybe you could put up a thumbs up sign or just wave or something so that I know that we can move on. All right, we got 1, 2. Excellent. Thank you all. Okay. Is anyone having issues running these? For some reason, it does not create the directory. That's interesting. So what the expected outcome of running these is that, did it throw an error or did it just silently not create stuff? You should also feel free to unmute and just speak. File not found. At what point did it throw that error? Is it when running this one, or change the yield modeling tutorial and then change to yield? Sorry, we're running.
I see you. What are you doing up here, buddy?
Hey, Rhonda, you're not muted, just so you know.
Oh, thanks. I did not know. I actually ran into the same error, and I'm trying to remember what my fix for it was.
So I'm trying to.
I think on my first attempt, I actually had a typo when I tried to copy paste the string of the suggested directory. I think I didn't grab one of the characters.
So
Um,
you shouldn't need to you should not need to modify anything in here. If you did, then that could potentially be causing issues. So wait, run the next cell to change to the yield mod. I don't even see that. Are you in
there was
the tutorial itself? I'm a little confused as to where you are. I'm sorry. Uh,
Sorry, I wasn't in the tutorial. Sorry.
okay, so you're fine. You're totally fine. Okay, so you have to run the setup first before you can do the tutorial. So go through the setup and hopefully that'll fix things. Is anybody else having any issues? Okay, so Marcella, try to catch up, please, and we're just gonna pop over to the so once this is done, this never needs to be run again. In your drive, it should have created SSW, and then within there, there will be a yield modeling subfolder, and within there will be the Git repo. So that's just a way of verifying. Okay, and then once you're done with that, you can click the hyperlink at the bottom of the setup, or you can go back to this document and click the link to the actual tutorial itself, and that'll pop up a new collab page, and then you run, again, execute all of the orange cells. And so again, you need to remount Google Drive from this workbook. You need to specify the directory. So if you modified anything, then you would need to modify it here as well. And then you need to actually install everything. And so the installation takes a couple of seconds. And then you just keep running until you get to the tutorial setup. So I'll give people a minute to get through all this. But the goal is that you are executing everything that is tagged orange or orange and blue up through the learning outcomes section. So please give me a thumbs up when you've gotten there. Thanks, Denise. All right. Anyone hitting any issues?
Sorry, yes, I am a little bit confused. From the setup notebook, do we have to run the cell to install the tutorial on our own computer, or can we
No.
skip that?
Yeah, this is, if you're using Colab, then you skip those cells that are only tagged in blue.
All right. Thank you so much.
Yeah.
Yeah,
So
thank you.
there's two ways of running the tutorial. One is an offline install, and one is through Colab. And so Melanie has very helpfully put together these instructions that are tagged, right? So anything that's orange, you do for Colab. Anything that's purely blue, you do only for offline. And anything that's both, you do for both.
Got it. Thank you so much.
Yep. So in the Colab version, the installation happens within the tutorial notebook. That's what this cell is doing. And the only reason why we're installing anything at all is really just to it's the easiest way to package the required data. All right. How are other folks doing? Okay. Is anyone stuck or is anyone still waiting on stuff? Can I move on? Good. Okay. I'm going to move on. If it's not working for you, please call out right now so that we don't leave you behind. Okay, so the rest of this is just like there's a lot of words on the day. I think it's important to make clear that people don't have to read every word, they can skim, but buried within the words are equations that they're actually going to be asked to implement. So you know, you can skim, but pay attention to the equations. And it's supposed to be fairly linear in terms of the way that it's laid out, but you can skip forward. Like the doing downstream exercises is not contingent on finishing upstream exercises. They're all more or less self-contained. So that's another thing to point out. So if somebody gets to exercise 1 and is super stuck for a long time, you can encourage them to move on or look at the reference solution. For every single exercise, there is a reference solution, which is in the package that got installed. And the way to look at the reference solution is to go to, so on this left-hand side, as you probably know, you have a view that shows the table of contents of the cell itself, but there's other options. And this last one is a folder view. And within the folder view, you should have the drive mounted, your Google Drive mounted, so you can navigate to my drive, to the directory that got created, which is SSW 2024, to the yield modeling subfolder, to the tutorial subfolder, and finally to the, there's 2 of these, to this one that doesn't have the extension. And so within this, there is this Python file. If you double click it in Colab, it'll open up as a separate column. And so you can view these side by side. And within these, there are methods that are reference solutions to the various exercises. So for example, for exercise 1, calc_s_dmag, which is the first method in here, is the reference solution. So at any point, if anybody is completely stuck and they want to see what the reference solution looks like, they can just pull up the code, right? Make sense to everyone? Okay, so at this point, I don't know, Melanie, do we just let people start working through it and ask questions, or what's the usual approach?
It's sort of, it's however you would like to go through it. If you want to, I think other people have kind of gone through and talked through it, but I guess, I guess there's
Sure, I can talk through it, and then people can ask questions, and then if you'd like to start working on any of the pieces to see how they work, you can do that. Okay, so the flow of it is, so this is a tutorial about direct imaging yield modeling. I guess we should have moved that. So this is explicitly how we estimate the expected science returns of future space-based exoplanet imaging missions, like the Habitable Worlds Observatory. So the motivating mission for all of this is the Habitable Worlds Observatory, which hopefully all of our students will have heard of at that point. And of course, there's going to be the precursor talk by Chris Stark to introduce some of these concepts. And the idea is that we build up the essential elements that are necessary for yield modeling. And so the start of this is talking about the physics, the fundamental physics of exoplanetary systems. And so this first bit explains how we treat exoplanet orbits as 2-body orbits or ideal Keplerian orbits. There's this giant diagram with all of the things marked and labeled. And then the first bit of text just goes through some basic orbital mechanics to lay out the equations for the direct imaging observables. The direct imaging observables are the projection of the star-planet vector onto the plane of the sky of the observer. So this S vector here, that's the one thing that we can detect with imaging. And then the second one is the difference in brightness, or the ratio in brightness between the star and the planet, which there's an equation for lower down. And that quantity is called delta mag. This first code block is just to be executed. It calculates some of these equations for you. So this is the components of the 3-dimensional orbital radius vector. And then there's a few more symbolic computations, which eventually get you to the magnitude of that projected separation, which is, again, one of our observables. So this is one of the things that we can detect with exoplanet imaging. And so this is one of the things that we need to simulate. And the next bit, as I said, is delta mag, which is this rather ugly-looking function, and it is a function of the orbital parameters, as well as some planetary parameters, the geometric albedo and the phase function. And for the phase function, we'll be using a specific functional form. This describes the amount of light that a planet happens to reflect, given the geometry between the star, the planet, and the observer, which is encoded by the phase angle, which is called beta. So the first exercise is to first define some quantities, and then to actually implement code to compute all of the relevant things that we want to compute. So the students are asked to compute the orbital radius magnitude, the argument of latitude, the magnitude of the projected separation, the phase angle, the phase function value, and finally the delta mag. And so equations for everything in exercise 1 are given in the block above. So they finish that, they run it, and then, so I'm going to just run the reference solution so that I don't have to copy and paste text. And again, this is a way of basically just skipping out of an exercise. You can just run the reference solution. And then once you have the values, you can plot them. And there you go. So this is the first kind of check that things are going correctly. So what this plot is showing is the projected separation, that S value, as a function of the true anomaly, which is the angle of the, which is the angular position of the planet in time. And then the other shaded curve is the difference in magnitude as a function of true anomaly as well. So if the students have properly implemented this exercise, then this plot should automatically come out looking like this. Any questions so far? Fantastic. Exercise 2 is to establish observability limits. So remember, these are the two things that we observe, right? Our ability to observe them is limited by our instrumental constraints. And the primary instrumental constraints are there's an inner working angle and outer working angle, which when scaled by the distance to the star, gives you the range of projected separations that we can see. And then there is, there's also a limit on the delta magnitude that we can accomplish. So there's like a minimum brightness to the planet that we are sensitive to. And so the next step is implementing logic that applies those limits to these curves that we just calculated. So we provide values, right? An inner working angle, an outer working angle, and a distance, and we provide a delta mag limit. And then the second exercise is to compute which subsets of those two arrays, the array of projected separation values and the array of delta magnitude values, are actually observable. So again, I'm just going to cheat and run the reference solution. So, like so. And then this next block of code updates the previously created plot. So if we go back, now we can see here are our limits. So here's our delta magnitude limit, and then here's the projected separation, the inner working angle limit. The outer working angle limit is actually way off the scale of the graph, so you can't see it. And so the shaded, now the highlighted regions of these two curves are the points in time when we could see this particular planet with this particular instrument. Everybody on board so far? Hopefully. Okay. And then the last part of this section is to evaluate what happens as we allow the orbit to be arbitrarily oriented in space. This is just creating a plot for them. There's no exercise here. So when you execute this code block, you get the same figure, but now there's a slider. If you move the slider, you're changing the inclination, and you can see how that impacts the curves, and the limits stay the same, the curves change, and so the observable regions change. And you can see that as you go to lower and lower inclinations, your planet becomes observable everywhere. So a zero inclination is called a face-on orbit. That's where the planet is at the same viewing geometry for all time. And so if you can see it at one time in reflected light, you can see it at all times. if you go all the way to 180 degrees, that's flipped the other way, so it's the same thing. And if you're in the middle at 90 degrees, that should be the middle, then that is what's known as an edge on orbit. And this is where you will have the most variability in terms of when the planet is visible versus when it's not observable. Okay, so that finishes off the basics. Any questions from anyone? Okay, so the next bit is some fun statistics. What do we do with all this? Well, we define a population of planets, and then we sample that population, and then and then we create a joint density function of those two observables, of the projected separation and the delta mag. So this section describes in detail what the various distributions of the input parameters are and why that is. So this provides distribution for the probability density function for the inclination. The probability density functions of the other angles involved are uniform. And then we also need a density function for the true anomaly, which we get by first computing a uniform density function of the mean anomaly and doing some math on it. So again, for the details, you have to read the text, but the basic idea is that we're grabbing the equations and density function definitions in here, and we are implementing them. So that's exercise 3. We're going to generate 10 to the 5th samples from all of these distributions. We're going to fix the radius of the planet to 1 Earth radius, and we're going to fix the geometric albedo of the planet to something that is vaguely Earth-like. There's a link here to the NumPy random number generating functions, which if people are not familiar with how to generate random numbers, you should tell them to go read this documentation. But it's relatively straightforward. It's we have most of our distributions are either uniform or can be computed from uniform distributions. And so you see the very first thing in here is random.uniform. So the solution to this exercise is based on drawing a bunch of uniform samples and then manipulating them algebraically. So again, I will run the reference solution. Like so. And then this next bit generates, okay, so this next bit does some of the harder computations so that people don't have to implement it on the fly. And then finally, this plots the result. And so the expected output of this is going to look something like this. So in this case, it's really important to remember these are random draws. So no two people's plots are going to be identical. We're looking for the basic shape of this because we are doing random draws. The key thing to take away from this is that we are not, with only 10 to the 5th samples, we are absolutely not filling in the actual phase space because it's very large and we don't have enough samples. So we fix that by pre-computing a bunch of stuff. This just plots. So the first thing to point out is that we know that we're not filling the space because we can analytically compute the bounds of this density function. And that's what this piece of code does. So there you go. So this is the full area. This is the full region that should be filled in if we sampled sufficiently. And clearly 10 to the 5th samples is insufficient. So to fix that, we provide data, and that's what this block of code does. It reads in a pre-computed data set, which has 1 billion samples, and then it replots it, and now you can see that with 1 billion samples, we are fully filling in this phase space. So what this plot represents is the joint density function of our two imaging observables. It is the probability that a planet drawn from the population that we've just described falls in a given bin with a given delta mag and projected separation value. On top of this, we can apply our instrumental limits, and then we can marginalize the density function or integrate the density function within the instrumental limits, and that provides us with the value that we're interested in, which is called completeness, which is the next section. Any questions? Okay, So completeness is the marginalization of our joint density function within specific limits, a minimum projected separation and a maximum projected separation, and then 0 to our limiting delta mag. And we implement this as a Riemann sum, which is just a summation over that grid. And this figure just illustrates that bounding box. So this is what it looks like. So the completeness for a given instrument for a given population of planets is the integral of this color map of this heat map within the bounds of this box. And so the next exercise is doing that integral or approximating that integral. So again, I have hinted very heavily that they should be using a SciPy function from the interpolate submodule. There's a link to the documentation for it here. Essentially, this creates a interpolant over rectangularly spaced grid data. And then from that, it has helpful methods that allow you to evaluate integrals of that. So let me just pull that up. So this is the rect bivariate spline object, and its methods include an integral method. So that's essentially what we're trying to get the students to do. Create the spline and then use its built-in integral method to compute the Riemann sum. Okay, so I will just run the reference solution, and as it says, the expected output is 0.42. So the key thing here is what this number represents is our attempt to capture the probability that given a particular instrument description and a particular population of exoplanets of interest, in this case, roughly Earth-like exoplanets, what is the probability for a specific target that we will see a planet from that population, given that it exists, at our first arbitrarily timed observation? And the way that this exercise was set up, the answer is 42%. We have a 42% chance, if this star has an Earth-like planet orbiting it, we have a 42% chance of seeing it, right? And that's essentially what we're trying to do here, is we are trying to compute that probability, and then later on maximize that probability. Everybody good? Okay. So this value is highly dependent on many of our input parameters. And of course, a very important input parameter is the distance to that target. So this basically just creates another one of those interactive plots where if you drag the slider, you are changing the distance to the planet. And on the right-hand side, it is plotting out the completeness curve. So this works slightly better offline than online, but it looks like it's still basically working in Colab. So the idea is, as you move the star further away, you are moving the projected inner and outer working angle outwards, because the projected angles scale linearly with stellar distance. So as you move this bounding box outwards, you're essentially moving it out of the population, out of the phase space that the population takes up. And so your completeness craters. There's a sweet spot, which for this particular population occurs at just, I think it's like 6 or 7 parsecs. Something like that. Yeah. Yep. There you go. So yeah, so it peaks at 6 or 7 parsecs. For those of you who know about the distribution of nearby stars, there's really not that much within 6 or 7 parsecs, right? There's our nearest neighbor, Alpha Centauri, and then a handful of things, none of which are particularly great targets, and nothing. So if we're looking for Earth-like planets, we, don't have a ton to work with. Again, this is very specific to the inputs that were used to generate this particular plot, but that's actually a reasonable conclusion, is that looking for Earth-like exoplanets is quite hard. Okay, the other thing that makes a big impact on that completeness value is if we're modeling Earth-like planet populations, then we don't actually want the population of exoplanets fixed at a specific distance from their host star, because host stars have different sizes and therefore have different intrinsic brightnesses and therefore pump out different amounts of energy. So what we actually want to match is the insolation distance. We want to match how much radiant flux from the host star is hitting our Earth-like planet. And we accomplish that by scaling the semi-major axis of the orbit of our Earth-like exoplanet by the square root of the luminosity of the star, measured in solar luminosities. So for a sun-like star, Earth would be at 1 AU. For a star that is twice the luminosity of the sun, the Earth would be at a square root of 2 or 1.4 or so AU, and so on, right? And so this is what's known as a basic habitable zone definition. And so this is how we're going to do it. And the point here is that we do not need to recompute our density function every time we make a change for a different target star luminosity. Instead, we just reinterpret the axes such that this axis is scaled by the square root of the luminosity. And this axis, because it's already on a logarithmic scale, we add or subtract a function of the square root of the luminosity. And that's what these equations are telling you here. And so exercise 5 is taking the previously written completeness method and just adding a new input to it. So you reuse a lot of the code, and you literally just are adding this luminosity scaling. So I will run the reference solution just to show that it works. Oh my God. No, I do not need AI. Barely have any normal intelligence. And as it says, the result is 0.258. So this is using exactly the same inputs. What has changed is we are positing that this is a star that is 1.5 times as luminous as the sun. And if you recall, previously our chance of seeing a planet, an Earth-like planet, was 42%. Now it's suddenly gone down to 26%. And the reason for that is that our entire population has now moved outwards from the star, meaning that more of it is going to be outside of our outer working angle. And also it has pushed the distribution down, meaning that more of it is going to be above our contrast limit. And so this bit here illustrates that by generating another interactive figure. So this now changes the luminosity. You can see that for a very dim star, this is like an M dwarf, the bounding box lies entirely outside of our population. As we start to increase the brightness of the star, the population moves into the bounding box, our completeness becomes non-zero. It peaks for a particular value of luminosity, which is less than 1 solar luminosities, and then it shrinks again as the limits move the box downwards and eventually hit 0 again by the time you hit 30 sun luminosities, which is like a really bright A star. Any questions? Okay, so that's it on kind of the astrophysical side of things. And then the next bit is we're turning to the instrument side of things, because we have been assuming this whole time that we know what the limiting delta magnitude is that allows us to draw our bounding box to calculate completeness. But in fact, this is a function of how much time we choose to observe a given star, right? We collect more photons, we get more signal, we can actually dig deeper and find dimmer planets. So what is needed is an integration time model. Real integration time models are unbelievably complicated. So this section gets a bit, it gets a bit into the weeds. So again, encourage people to skim and just focus on what the equations are telling them. But I promise you this is as simplified as I could make it while still retaining any kind of fidelity. But essentially, signal to noise ratio, which is our metric of detection, goes as the square root of the integration time. However, if you just assume that, then the conclusion you reach is that you can hit infinite signal to noise ratios by going to infinite integration times. That's not physical. There are fundamental instrumental limits that mean that at a certain point, there's no more benefit to integrating longer. And that is modeled via an instrumental noise floor. And mathematically, we do that by introducing this extra term to our SNR equation added in quadrature to the noise variance, which is the definition of the noise in the SNR. And so you get this expression, which means that you have a specific condition on the relationship between that noise floor term and your expected planet counts and your targeted SNR. And so all of this together allows you to compute integration times. which is exercise 6. So implement the method given the planet count rate, the background count rate, the noise floor, and the target SNR. What is your integration time? Okay, because of this constraint, there are infeasible integration times, right? Like you can set up a set of inputs that lead to this going to negative, right? Which is non-physical. So what that means is just you ask the system to perform beyond its capabilities. And so in the code, the comment is that these should be set as not a number values. And in fact, there's just a code block that already does that for them. So that all they have to fill in is the equation here. So we'll run the reference solution. And there you go. As it says, the integration time is almost half an hour, right? So these are not quick observations. This is actually a small integration time for exoplanet imaging. This is a slightly non-physical setup where all these values are very, very nice. But yeah, so that's an important thing to take away from this is that exoplanet imaging, especially if you're going after Earth-like exoplanets, there's going to be many minutes to hours to potentially even days of integration time to get the signals that we need, because literally we are talking about photon arrival rates of single digits numbers of photons per second or minute or even hour. So it's real hard to build up this signal. Okay, so we now at this point have a way of calculating integration time if we know what the expected count rates are for the planet signal and the background signal, but now we need to know how to model those count rates. So that's what the next section does. So this is modeling. So we're now modeling planet and background counts. So Melanie tells me that this symbol renders properly in her browser. Are people who are following along, do you see a calligraphic script F here, or do you see a little box like on my screen? Okay. Okay, so this is something very specific to my browser, which is bizarre. But that's great. That means I don't need to change anything. Okay, fantastic. So you all see the proper thing. So this is going to be our model of this count rate, right? So the star has a magnitude in your given observing band. If you do 10 to the magnitude of the star divided by negative 2.5 times the zero magnitude flux, then you should get the counts due to the star, or the flux, rather the flux rate, flux density of the star. The planet is then that scaled by the delta mag, right? So you could just add the delta mag in the exponent here, right? If you're observing a 5th magnitude star and your planet has a delta mag of 25, then the planet is a 30th magnitude object, right? So that's the way to understand this expression. The actual number of photons that you register is then also mediated by various instrumental effects. So you are sampling a finite sized area, so you need to scale by the area of your primary mirror, that the actual effective collecting area minus any blocked regions. You are collecting photons within a very specific bandpass, so you need to scale that flux density by the delta lambda, the bandwidth. You have throughput of your entire optical system, not including your coronagraph or starlight suppression system. And then you also have this tau core value, which is the throughput of our coronagraph or starlight suppression technology specifically for point sources like planets. And finally, you have the quantum efficiency of the detector, right? Because it's not necessarily one electron or one data number per photon registered, although we do have some devices that attempt to do that. But there is a quantum efficiency involved as well. This is how you calculate the effective area of your primary mirror. And yeah, just to make things cleaner, because we're going to be using this set of multipliers over and over again, we can package the area, the bandpass, the non-chronographic throughput, and the quantum efficiency all into one efficiency term that we call eta. And that's just used to clean up the expressions. So that gives you the foreground count rate, the planet count rate. You can do exactly the same thing for the major contributors. The background count rate, the major contributors are the light from the local zodiacal dust cloud that the Earth is within in the inner solar system. We also assume that other systems have similar clouds. So you have a component of the local zodi and you have a component of the exozodi. In order to compute those, you need to assume a nominal brightness of that zodiacal cloud. And so that is done through this Z value, which has units of magnitudes per square arc second. You then need to compute the photometric aperture that you're actually using, because that's the number of square arc seconds that you need to scale this by, and that's given by this expression. And finally, there's the residual starlight that leaks around your coronagraph, and it has a very similar form. You're basically just scaling the star by the contrast level, and then all the other terms. Finally, there's the contribution of the instrument, of the detector itself. The detector has two main noise contributions. They are the dark current, so that's the rate at which you accumulate electrons even when your detector is not illuminated at all. And then there's the read noise, the number of electrons that you pick up as you're reading the photons out of your detector. And so there's expressions given for each of those, and they are a function of the number of detector pixels that the planet lands on. Okay. So that gives you the CP value and the CB value, the foreground counts and the background count rates. And then we need that M term, which is our noise floor. And that is modeled by the speckle residual multiplied by a post-processing factor. So we're keeping things really simple. If anybody's seen more in-depth integration time models, like, you know, there's a lot more that usually goes into these. Okay, so that's it. So that brings us to exercise 7. Which is, again, to just implement all of the above. And so because of the huge number of inputs, we are packaging them into 3 dictionaries. So people might want to spend some time poking around and figure out if they're not super comfortable with Python programming, how to access these, how to do things with them. So you should encourage people to use this space. Thank you, whoever suggested that. Thank you, Melanie. Okay, great. It's gone, hopefully. Okay, so yeah, so we are going to be operating in the visible, so that's 500 nanometers. We are doing an HWO-like aperture, so this is a 6 meter primary mirror. So this is the lambda over D unit, which is the kind of the fundamental angular unit that describes coronagraph performance. And so you can see that 1 lambda over D for this scale of aperture and this wavelength is a tiny, tiny angular value. But that's, and just for reference, the reason why we care about this is because like a really good coronagraph will have an inner working angle of something like a few lambda over D. Like that would be a phenomenally good coronagraph. And so that just means that your inner working angle is tiny, tiny value, but then you're scaling it by stars that are quite far away. So that's the reason why these numbers are important. And then we define the rest of our setup with these 3 dictionaries. So we have parameters that we do not expect to change between observations. We have parameters describing the coronagraph's performance, and then we have parameters describing the particular target, right? So again, if various students are unfamiliar with how this is supposed to work, you should encourage them to, you know, try accessing these. So for example, if I want to get at the lambda value, I can access it this way. If I want to get at the one of the coronagraph parameters, contrast value, I can get to it that way, and so on. And so they will need to be able to do this in order to write the code in the next function, which is literally implement all of the equations from the previous couple of sections. So this tries to lead students through this systematically. All of these values have units. So there's some implementation notes about units here that if people get stuck, they should go back and read. But anyway, like hopefully it's laid out in a fairly straightforward order. So this lets them check Oop. Ah, my bad. No. Ah, this doesn't actually output anything, which is not great. There we go. Okay, so as it says, our planet count rate, so this is the expected counts per second due to the planet, is 0.015, right? So we're talking about 100 seconds to get one count due to the planet registered on our detector, which is actually representative of this kind of observation. Our background count rate is actually higher. And one of the counterintuitive things here, at least to me, is that like it's hard to figure out how you can actually build up signal to noise when your background counts are higher than your foreground counts. This was always throughout my career something that tripped me up, right? But the idea is that they're describing two different things. Like the background count rates are kind of just this undifferentiated mass of background that's streaming at your detector, whereas the point source is just in one location. And so if you can adequately model the background, you can just subtract off all of what that background is doing and still accumulate specific signal due to the planet. That can work up to the point where you hit the instrumental noise floor, at which point the background is varying enough that you can't subtract it off, essentially. So the noise floor is just another way of, it's a way of making a statement about our inability to subtract away that background.
So Dmitry, are you saying that the background counts here are not distributed over the same point source as the planet, but there's like a different area term involved here?
Well, no, sorry. So this particular count rate is yes, it's scaled by the number of pixels of the photometric aperture. So it is for the same region, but I'm saying that it acts as a piston to the signal. And so you can still differentiate between it to us up to a certain point. I don't know. Rhonda, if you have a better way of explaining it, please step in. I feel like I've been talking way too much.
I don't have a better way of explaining it, except that it really comes down to the post-processing, right? Because if you have and really it comes to what we're really doing is you can average background statistically over time. And then the real problem comes for us is noise that does not improve with integration time, which is what the speckle usually is, and why that's the limiter to the noise floor. But that's not the point that's being made right here.
Yeah, I mean, I was just trying to kind of, perhaps this is, it's only I who get confused about this, and it'll make perfect sense to other people. But I think that when I see that my planet signal is smaller than my background signal, it leads me to wonder how I'm ever able to detect the planet. And the key point is that this background signal is subtractable up to a variance of this magnitude. And that's what sets the map.
That's
and
a
that's
great
what
way
sets
of
the
saying
noise
it,
floor.
Dmitry.
Right. So up until I hit variances in this at the fourth decimal point, I'm able to subtract it away. Once I'm there, once I've integrated long enough to be able to discern that fourth decimal point, then I'm done. Right.
Mhm.
And so when you put all this together, you get an integration time of almost 1.5 hours. Or yeah, 1.25 hours. And again, that is a completely reasonable, based on our predictions about how something like HWO will function, that's a very reasonable integration time for an Earth-like exoplanet detection. All right. Yes, and this is just doing a consistency check that shows that our maximum possible SNR is going to be 25 for this observation. Okay. So last bit on completeness. We need to calculate the integration time so that we can compute the effective delta mag of planet that we can achieve with a given integration time, so that we can calculate the completeness of that observation. And in order to follow through that process, we actually need to be able to invert the integration time to calculate. So the equations that we set up here compute integration time as a function of the input delta mag, which comes in through this step. We now need to invert that so that we can calculate the delta mag for a given integration time. And that's what this section describes, and it's literally just an algebraic inversion of the previous set of expressions, and then exercise 8 is implementing that algebraic inversion. So it just runs through it, and if we look at the results, I keep forgetting to do that. Why? There we go. And again, this doesn't actually print anything out. That was sloppy on my part. Apologies. There we go, 26. So this is just a demonstration that we can get back the input that we put in. So 26 delta mag was the original input to our integration time all the way back here. Right, you can see it at some point. Sorry. If you scroll back far enough, you get that input, or perhaps I even redefine it. Oh, I redefined it here. I'm sorry. So we put in a 26 delta mag, we calculate all the count rates, we calculate the integration time, and then we use our new method for inverting that to get back the original input, which was 26. Okay. Any questions? Okay, I'm just going to power through to the end. Our end goal is to try to do these kinds of calculations for an actual mission. And so for that, we need a target list. We're going to be using a target list that was published last year, or no, earlier this year, I guess, by the Exoplanet Exploration Program Office, and specifically by Eric Momacek and Carl Stoppelfeld, who created what they call the HWO mission star list. So this pre-written bit of code loads the targets. And so here you can just see a few rows. This is a giant data table that has everything you want to know about these targets. The thing that we care about specifically, we can calculate the completeness for all these targets. And so this calculation based on pre-written function is all of the completenesses of all 164 targets, and the print statement here is just showing us the minimum completeness, the maximum completeness, and the mean completeness. So we see that for these 164 targets, which were identified as kind of the best set of targets based on a lot of different assumptions for something like HWO to look for Earth-like planets, we have targets ranging from an almost 0 probability of detection to quite high probability of detection, and the mean probability of detection hovers right around 20%. So this is another reason why exoplanet imaging is hard. Most of the time, you're just not going to see anything. So this tries to visualize that data. And so the plot that is generated here is a map of the sky, and you can see, so these are the 164 targets, and the color scale is the calculated completeness. So there's not a ton of systematic structure to this. It's driven by the target luminosity and the target distance, right? So there's no particular distribution of those within the local volume, so it's kind of random where the high completeness targets end up being. Okay. And now let's see how long it would take to make those observations. So we set up a slightly more realistic coronagraph that's slightly less performant than the last one that we tried. So its contrast is a little bit lower. And then we compute the integration times, and then we plot the integration times as a function of the target's magnitude. And you can see that it's almost linear in log space, which is exactly what you would expect. And the total integration time for all 164 targets for this particular system description is over 6 years. So if you have a 5-year mission, it is literally impossible with the coronagraph that we've described here to just do detection observations on each of these 164 targets.
And that's, Dmitry, that's a single detection observation on every one of
Correct.
these targets.
Yeah. So this does not describe a credible mission at all. This is literally like if I pointed my observatory at every one of these targets and just integrated enough to get to a delta mag of 25, how much time would I need for that? And you can see it's a lot of time. Like a lot of these take a long time. And obviously now comes the creative part, is how do you select the subset of these targets that are actually worth looking at? Like, I think we can all agree that spending 10 to the 7 seconds on any one target is probably silly, right? But where should you put that cutoff? How should you go about deciding which of these targets are worth going to and which of these are worth re-observing? And that's the whole crux of mission modeling for exoplanet imaging. Okay, so we're getting to the point where we can actually start building these mission models. The last bit of things that we need to consider are the constraints. We can't observe targets at arbitrary times. And there's a bunch of different reasons for that, but the basic reasons are the local geometry of where our spacecraft is in the solar system, right? So our spacecraft nominally is in some halo orbit about the Sun-Earth L2 point. This is a representation by of the synodic frame or the rotating frame. So the x-axis always points from the sun to the Earth to the Lagrange point, right? So the x-axis is spinning in three-dimensional space about the y-axis, which is essentially ecliptic north. Okay, so the telescope is on this halo structure about L2. The telescope may be flying with a starshade, or it might just have an internal chronograph. Regardless, it cannot point anywhere towards the sun, right? So this region is excluded. So the telescope can only observe stars that are in this white region. If the telescope has a starshade, it also can't point directly away from the sun, because then the sunlight would reflect off the starshade. And so alternatively, if the telescope has solar panels that are mounted parallel to the bore site, it also can't roll away from the sun. So it has similar types of exclusions. So there's a lot of different things in play, right? And the way that we encode all of that is by generating a keep-out map. And this is something that's pre-computed and part of this package. So we can load it up and take a look at it. So the way that you read this is the x-axis is time from some nominal mission start, and the y-axis is our targets, right? Those 164 targets from the catalog. And it's a Boolean array. And so the parts of the array that are true mean that you can go, your target is good to go. And the parts that are false means that the target cannot be observed at that point in time. There's structure to this, which we can get at by sorting the targets by their ecliptic rather than equatorial coordinates. And so it is basically strictly a function of the ecliptic longitude when these observability windows are. And the duration of the observability windows is a function of the ecliptic latitude. And we can plot that like so. So with the specific keep out that we've generated, the high ecliptic targets, right, so things that are down at the north and south, at the south and north ecliptic poles, they're visible for half a year at a time. And everything else is visible for less than that, down to a minimum of just about 100 days out of every year, so less than a third of the time. Okay, so the final exercise is using the keep out map to check on when targets are available. So people are asked to implement the given the keep out map and the associated times, and for a specific set of target indices, and for a specific set of observation start times and observation durations, which of those targets will be observable. And so, right, and then if we run the reference solution for the check, yeah, that the result, you can see that of the 3 targets, the first one is observable and the other 2 are not, because of the way that the inputs were set up. And this explains exactly why that happened. Okay, that's it. That's the end of the tutorial. There's obviously a lot in here. I had 2 undergraduate students run through this a couple of weeks ago. One of them took 3 hours and one of them took 20 hours. So I'm expecting a very wide range of completion rates. It's not strictly necessary to get through everything. You should encourage people to skip ahead if they're stuck on a thing, and really focus more on the conceptual stuff in here.
Thanks, Dmitry. Just going to open up just if anyone has any questions, Nice to meet you now. Just a reminder, there is the Slack channel again, as I mentioned before, the private one with for the helpers, and then I'll be adding people to that channel as I go through, just make sure from the list I have, and then we'll be posting the recording on our SIGIN workshop YouTube channel as well.
All right. Yeah. Any Marcella, if you're speaking, you're muted. No, okay. No worries. Okay. I guess I'll just add that is there right. So there's group projects based on all this that are in a separate sheet that you can take a look at. They are completely open-ended, and essentially there's two of them. The first one is using all of the machinery that was built up in the tutorial, try to actually do that time optimization that I was talking about. Try to figure out how to allocate integration times to different some subset of your target list to maximize the overall completeness. And again, this is completely open-ended. People can take any approach they want to. There are some links in here somewhere to various papers that talk about various approaches to this, but people can do whatever they want. And then the other project is try to actually craft an observing schedule based on specific mission constraints. So that is take pre-allocated time for each target and then try to align it with the keep out map within the constraints of a overall mission time. And again, totally open-ended. There's some links to relevant papers, but people can take any approach they want to. So hopefully some people will choose to work on that and we'll have fun with it. Okay, that's all I got.
Thanks, Dmitry, and thanks to the helpers too. We really appreciate your help. It's nice to have people be able to ask questions either on the Slack channel or if you're in person. This is a really great service to provide for the attendees. And again, you're welcome, please, to just participate in these sessions and group projects as well.